A primary task of VELA uniform called for the establishment of a worldwide cooperative seismological research network. In all, over 100 stations are involved, girding the Earth with calibrated and standardized instrumentation so that for the first time, the findings of any station can be confidently compared with those of the rest. The first station to become operational was in 1961, the U.S. Coast and Geodetic Survey's seismic laboratory in Albuquerque, New Mexico. 21 months later, this modern equipment was operating in 48 countries and territories. The Albuquerque laboratory is a key link in the network. It supplies station equipment, trains geophysicists for installation and maintenance of other stations, repairs equipment, and provides troubleshooters for station difficulties. The basic equipment for each station consists of 3 component seismometers, recorders, a timing system, calibration system, copying equipment, and a power source. Package cost, approximately $20,000. Free to each station with no obligation beyond maintenance, operation, and free exchange of data. Another major task of VELA uniform has been the planning, building, and operation of advanced prototype seismic observatories in the United States. These were specifically designed to detect, identify, and locate nuclear explosions. There are 5 of these stations located in low-noise areas to take advantage of seismic signals from past and projected underground explosions at the Nevada test site, at the New Mexico site near Carlsbad, and in the Tatum Salt Domes in Mississippi. Distances from the Nevada test site range from 300 miles to 1,600 miles. These observatories follow the practice of using a single seismometer to detect seismic signals. Instead, they all use multiple element arrays up to miles long on a side, as in this generalized illustration. A number of seismometers are hooked together in various ways to permit complex electronic processing of their signals to make a single record. This tandem technique may improve signal-to-noise ratios by a factor equal to the square root of the number of seismometers. In our example, the square root of 9 elements gives a possible 3-to-1 improvement. 4 of our 5 stations are basically of the type proposed during the earliest Geneva technical discussions in 1958. These seismological observatories are named, respectively, Blue Mountains, Uinta Basin, Wichita Mountains, and Cumberland Plateau. The Blue Mountains Observatory in Oregon is located on granite in a very rolling region. Its 10-element array is simple in design. Utah's Uinta Basin Observatory is situated on sandstone within a flat intermountain basin. This 10-element array is a more complex design. The Wichita Mountain Seismological Observatory on Oklahoma granite was the first of these Geneva-type observatories to become fully operational, which occurred in October 1960. This array also has 10 elements. It should be noted that in addition to the main 10-element array, each of these standardized observatories also has 3 component installations for detection of tremors at different frequencies than those concentrated on by the arrays. It takes miles of cable to transmit the electric signals from the various detectors to the amplifiers, after which the signals are recorded on 14-channel tape recorders, on photographic film, and on special heat-sensitive paper. The Cumberland Plateau Observatory on Tennessee sandstone is basically a Geneva-type station, but it also puts signals from a 19-element array through a velocity filtering process, which, under optimum conditions, can theoretically achieve signal-to-noise improvements some 40% better than the simpler array systems. Our 5th station is the Tonto Forest Experimental Seismological Observatory. It lies in an Arizona mountain basin, floored partly by granite and partly by limestone. This advanced station utilizes a 31-element array, which may later be expanded to 100 elements as our top effort in this type of system. The location of these observatories in remote areas to avoid man-made seismic noise made major construction problems unavoidable. Roads had to be built from scratch, and dirt roads and mud are almost synonymous. Cables had to be laid over heavily forested mountain regions. Deep excavations were necessary to place seismometers on solid rock in order to secure maximum signal pickup. In spite of these and many other difficulties, all 5 of the advanced prototype observatories were operational by early 1963. Also now operative, a Data Analysis and Technique Development Center has been established in Alexandria, Virginia. Its mission is to make effective use of the tremendous amount of unique data being gathered by the observatory arrays and VELA uniform mobile field stations. The facility is equipped for all requisite processing and storage of magnetic tape and film data, and for advanced research on location and identification criteria. Typical of the center's studies are those underway to determine detection threshold capabilities of the various research laboratories. In one study involving some 500 earthquakes, the 10-element array of the Wichita Mountains Observatory was able to detect about 90% of the P waves reported by the U.S. Coast and Geodetic Survey for seismic events 2,500 to 6,000 miles away, with apparent magnitudes of 4 or greater. 4 is the approximate magnitude of the seismic signal created by a 2-kiloton buried explosion in a typical soft rock formation at the Nevada test site. It is also considered as a sort of unofficial standard, since it is about the lowest level of explosion signal that we can reasonably expect to detect regularly at long range by presently considered detection networks. VELA Uniform has also sponsored activity in seismic research areas which have never previously received more than a small fraction of the brain power and financial support that this program has injected into them yearly since early 1961. These are the activities that utilize the bulk of the university, government agency, and industrial research effort we noted earlier. As background, it should be noted that many of the university research efforts have hinged on or obtained primary data from nuclear explosions at the Nevada test site. One promising Columbia University study compares the long-period surface waves produced by Nevada explosions with those from earthquakes of the same energy level or magnitude. Since comparisons of seismogram amplitudes are complicated by regional effects and wave distortions, a comparison of the areas enclosed by the envelopes of the waves has been tried. It develops that the envelopes of earthquake surface waves enclose 5 to 10 times more area or wave energy than do the envelopes of surface waves from buried explosions of the same magnitude. A limitation is that while well-developed long-period surface waves propagate to very long ranges, the detecting stations must also receive short-period signals in at least 3 directions from the source in order to calculate its energy magnitude with necessary accuracy and to allow for the large directional variations that characterize surface wave radiation patterns from earthquakes. A majority of the very shallow earthquakes in the United States occur in Central California. To study them, the University of California has established a local network of 9 stations which telemeter the signals they pick up to a central recording console at Berkeley via long-distance telephone lines. The objective is to determine whether earthquakes ever originate at depths shallower than 3 miles, since that is about the maximum depth at which man is likely to set off buried explosions. How do we go about determining the depth of focus of such a shallow seismic event? It has previously required a dense network of relatively close stations, and even then, the depth calculation could easily be inaccurate by 5 or 10 miles. One VELA uniform study on this subject has examined a technique suggested by a British seismologist, Dr. H.I.S. Thurloway. This technique applies to events at any depth in the crust and at distances up to some 500 miles. Computations are based on the arrival at a detection station of 3 successive wavefronts. First, the high-speed, deep-running P wave, then the direct crustal P wave, and finally, the slower crustal shear wave along the same track. Accuracy deteriorates if noise makes the arrival times uncertain, if the crustal base is slanted, or if the crustal velocities are unusual. Further research, including the use of calibration explosions, is actively continuing with the hope of eliminating these difficulties. In 1960, as part of VELA uniform, the U.S. Geological Survey instituted the largest effort in crustal and upper mantle studies ever undertaken within the United States. Centering their strata mapping work on the Nevada test site, by late 1962, the Geological Survey had obtained over 2,000 recordings of seismic waves from some 35 nuclear explosions and 86 chemical explosions, some at distances up to 650 miles. By this effort, profiles of seismic wave behavior were mapped along lines from eastern Colorado to the Pacific and from central Idaho to Mexico. We have learned that there are substantial variations in crustal and upper mantle wave velocities in the various geological provinces of the western United States, some of which are structurally very different from others. As a consequence of this geological complexity, when seismologists of Southern Methodist University ran a trial computation on the location of the Yellowstone earthquake of 1961, the use of older standardized travel time curves misplaced the quake some 50 miles to the east of its actual location. As part of VELA uniform, Southern Methodist is now conducting a study of seismic travel times across both American and Asian land masses. The preliminary United States map shows that the western states and the Aleutians are the most seismically complex part of our nation. Russia appears to have a roughly similar pattern, with greatest complexity and seismic activity in the Kamchatka-Kuril Island region. One of the most promising VELA uniform studies is testing seismometer performance in boreholes ranging from several hundred to 10,000 feet deep. In some cases, remarkable gains in signal-to-noise ratio of as much as 8 or 10 to 1 are being achieved, because a considerable proportion of seismic noise is a surface effect, which decreases with depth. On one occasion, a surface seismometer in Texas, using a magnification of 50,000, detected nothing aside from substantial microseismic noise. At the same site, a deep-hole seismometer, some 10,000 feet below the surface, found the noise so low that a magnification of 1.5 million could be used, clearly revealing seismic waves from an earthquake in distant Chile. A more elaborate setup in an abandoned oil field near Tryon, Oklahoma, involved a total of 15 deep-hole seismometers, 3 of them per hole in each of 5 holes, producing a 3-dimensional array with the lowest plane about 3,800 feet below the surface. In addition to signal-to-noise improvements, this system has proved able to detect within 3 or 4 degrees both the direction and angle from which a wave front passes through the array. To be usable in this work, both the deep-hole seismometers and their connectors and cables must be able to withstand for weeks at a time the 3 tons of pressure per square inch, 200-degree temperatures, and corrosive environment found a couple of miles deep in the earth. Another instrument under development is the deep-sea seismometer, potentially valuable because the bulk of Soviet seismicity occurs in the Kamchatka seaboard region, close to the international waters of the Pacific. One type of ocean bottom instrument is designed to telemeter its seismic findings as much as 100 miles to shore by deep-sea cable. In another type, intermittent recordings may be made for periods up to 3 months, then recovered when the instrument is hauled to the surface. Tests have been made off the California coast, in Arctic waters, and off the Aleutian Islands in depths up to 20,500 feet. It appears that signal detection performance will be equivalent to that of land stations having moderate sensitivity. In VELA Uniform's original planning, a series of underground explosions at the Nevada test site and elsewhere was to be tailored to the specific needs of the seismic research program. Shots were to be fired at various depths in different geological formations to produce signals for measurement programs and to check the effectiveness of the different media in generating and transmitting seismic waves. Tests were also to be made of the effectiveness of muffling or decoupling explosions to reduce the size of their seismic signals. Our previous deep underground experiments were all fired in a medium called tuff, a water-soaked soft volcanic rock, and the shot devices were tamped by refilling the shot holes, guaranteeing maximum coupling of the shock to the surrounding tuff. Theories were advanced that if the shots were not tamped, but fired in sufficiently large underground chambers, the airspace would decouple the shots, so that seismic shock waves would be reduced by factors as great as 100 to 300. At optimum, this could mean that a decoupled 100 kiloton explosion would produce smaller signals than a tamped 1 kiloton device, undetectable at relatively short range, and lost in any case among the seismic waves of literally thousands of small earthquakes of that size each year. In early 1960, Project Cowboy fired chemical explosions in decoupling chambers in salt dome formations in Mississippi. These were compared to tamped shots in the salt, with results that substantially confirmed the major aspects of the theory. Thereafter, our orderly shot program was abruptly set aside when the large-scale renewal of Soviet weapon testing in September 1961 led to our own resumption of testing. Fortunately, since our weapon development shots were fired underground, a considerable number of VELA uniform objectives could still be partially or substantially carried out, grafted as it were onto the urgent nougat weapons test programs of the Department of Defense and the Atomic Energy Commission in Nevada. By dint of rapid mobilization of contract and government agency facilities, seismic studies were possible from the start of the nougat series. By electronic instrumentation, surface and subsurface measurements were made of violent shock effects in the immediate vicinity of the deeply buried explosions. Vertical ground motion near surface zero was studied by high-speed photography of accurately aligned targets in that area. On almost all events, the U.S. Coast and Geodetic Survey made measurements with a row of seismographs spaced from within 2,000 feet of surface zero out to a distance of 90 miles. The mobile trailer units recorded a profile to the southeast for a number of shots, then swung around to the west to lengthen the profile coverage. Extensive experiments were made to determine whether buried nuclear shots emitted any long-range electromagnetic pulses, but no significant signals were detected beyond about 20 miles. Other VELA uniform programs tried out on-site inspection techniques to determine whether suspicious seismic events could be identified as nuclear on the basis of surface indications. It was found that damage to root systems of shrubs and trees near surface zero sometimes causes changes in foliage reflectance characteristics. These changes may be detectable by aerial camera surveillance. Such surveillance would also quickly spot the surface hollows sometimes left by earth collapse into underground cavities created by deep shots in soft alluvium. Rock slides, ground fissures, displaced humus, mine openings, and even minute surface leakage of radioactive gases give clues to shot locations. It was estimated that the various surface techniques could locate a nuclear shot epicenter to within a few hundred feet, if other data could first direct the search to within a mile of the site, and if the detonation occurred at customary depths. Post-shot seismic monitoring provided data for comparison of the aftershock characteristics of earthquakes with those of explosions. It was concluded that explosion aftershocks are much more centralized and last only a few days at most, as against weeks for many earthquakes. The largest and most complex operation was the long-range seismic measurement program. Some 46 VELA uniform mobile seismic stations and another 5 mobile units from the University of Michigan recorded explosion effects at ranges of 45 to 2,500 miles from the Nevada site. Many additional recordings were made by observatories and university stations. Typical of the studies made were those on the Atomic Energy Commission's 3-kiloton Nome shot, fired approximately 1,200 feet deep in a bedded salt layer near Carlsbad, New Mexico. It was the first U.S. continental nuclear shot outside Nevada and the best recorded shot on record. In addition to permanent stations around the country, more than 90 mobile seismic stations observed on Nome, including some 39 volunteer units from the oil exploration industry. P-wave arrival times to the east of Nome were much earlier than at the same distances to the west. These travel time anomalies were the greatest ever observed in the United States, reaching as much as 12 seconds over a total spread of 2,000 miles. The wave strengths, or amplitudes, were also drastically affected in the two directions. P-wave motion at Jackson, Tennessee was 150 times greater than at Mena, Nevada. Measurements from Nome also indicated that explosions in a salt dome produce seismic signals some 2.5 to 3 times as large as similar shots fired in Nevada tuff. Seismic recordings from the hard hat shot, nearly 1,000 feet deep in granite at the Nevada site, showed that this rock is almost as efficient as salt as an energy coupling material. It was noted that hard hat produced strong surface waves, while those from Nome in salt were surprisingly weak. On the other end of the scale, it was learned that explosions in Nevada's soft, dry alluvium produced seismic waves scarcely 1/10 as powerful as if fired in tuff, or 1/30 of those in salt, and emitted almost no significant surface waves. This dry alluvium, in other words, has a built-in muffling capability to frustrate distant detection stations. Using data from a random group of stations around Nome and the Nevada test site, checks were made on the usefulness of standard epicenter locating techniques in such geologically complex regions. The stations were selected to fit a representative Geneva-type spacing of some 400 to 600 miles from the events recorded. Location errors on Nevada shots were of the order of 5 miles, but substantially larger ones were found in the Nome calculations. These located the epicenter about 18 miles east of the actual site, generating a potential search area of about 1,000 square miles, a much larger area than any considered probable during the Geneva test ban talks. Later calculations, making use of the newest VELA uniform regional data, reduced the 18-mile error to about 4 miles, a more acceptable value from the standpoint of a possible treaty. The last of the VELA uniform tasks involves the establishment of the VELA Seismic Information Analysis Center, or VESIAC, at the University of Michigan. VESIAC functions as a scientific information center. In addition to library and technical evaluation functions, VESIAC publishes such informative reports as the Periodic Information Digest, the Compendium of Contract Information, the Bibliography of Scientific Papers relating to VELA Uniform, Special Advisory Reports on Research Developments, and State-of-the-Art Reports by noted scientists. In summary, VELA Uniform has to date shown important progress in both main aspects of the explosion identification problem. It has spotlighted or confirmed substantial obstacles such as big hole decoupling, the large muffling of seismic signals by dry alluvium, and the lack of precision of some epicenter determinations. On the positive side, there is some overall easing of the technical problem. Our newest data predict less than half as many annual earthquakes of significant size in Soviet territory as previously estimated. Deep hole and ocean bottom seismometers can open new areas of the world to seismic surveillance. Our sensitive array systems can now consistently detect, at long range, seismic signals equal to those from tamped explosions in tuff of only a few kilotons. It must be noted that as yet no single reliable long-range identification technique is available. However, the new identification aids now appearing could, with cumulative evidence, direct strong suspicion at any substantial and continuing violation of a test ban treaty. Definitive checks on such suspicions could only be afforded by the adequate on-site inspection program which the United States continues to require. In the meantime, VELA Uniform goes rapidly forward in both laboratory and field in its pursuit of generating a sound technical answer to the scientific problems inherent in the construction of a comprehensive external detection system for underground nuclear explosions.